Question 36 from the heat topic. Figure 10.17 here shows the relationship between the temperature of 100 grams of an unknown substance and the time it is heated by a 1000 watt source. What is the melting point of the substance? So that can be read directly from the graph. Okay, so here these flat parts of the graph is where the substance is changing state. So melting or boiling. Now melting comes before boiling, so this is clearly the melting stage. What temperature is that happening at? 80 degrees. What is the boiling point of the substance? So this is the boiling phase. That's happening at 150 degrees. There's the answer. How much energy is required to melt the substance? So that's to get from here as a solid all the way up to here. So this is the melting part of the graph. So often the graphs just have energy on this axis. So this would be easy to read off. It just tells you how much energy. This one's a bit trickier. So it didn't give you the energy, it just gave you how much energy per second. 1000 watts equals 1000 joules per second. So it gave you that information, but also the time that the energy source was running for. So it ran for, well, melting started at 20 seconds and then melting finished at 150 seconds. So it took 130 seconds to melt. So if it's 1000 watts, which is 1000 joules every second, and it ran for 130 seconds, well, that's 130,000 joules. What is the specific latent heat of fusion of the substance? Fusion relates to the solids, so solid turning to liquid or liquid turning to solid, depending if we're adding heat or removing heat. So there we go. This is referring to the melting. We've just found the energy. There's the formula for the latent heat for melting or boiling or freezing, condensation, whatever. Q equals ml. So we just found the Q required to melt the substance, 130,000. The mass is given in the question, 100 grams, so that's 0.1 kilograms, times L. So therefore, we just divide both sides by 0.1. Sorry, I put brackets around when I substitute things in, so I should have put brackets around here too, really. It's just a good way to organise your information to show what's a substituted value. It's really handy for when you've got negative numbers to use brackets. Okay, let's keep going. So 130,000 divided by 0.1 is 1,300,000. Is the latent heat. Now latent heat's measured in joules per kilogram. So that one's finished. 1,300,000 joules per kilogram. What is the specific latent heat of vaporization of the substance? So this is this part of the graph where it's boiling. So same thing, we have Q equals ml. So this is part E, isn't it? That was part D. That was C, and A and B were easy. So Q equals ml. Now we know the mass. It's up here. We don't know the Q yet, but we can use the same process as in part C to find the energy required to boil this substance, because it took, well, it started boiling at 180 seconds and finished boiling at 1200 seconds. So 1200 take away 180 equals 1020. Okay, so 1020 seconds, it's 1000 joules per second, because remember it's a 1000 watt source. So we can say that Q equals 1020 seconds times 1000 joules per second. So that's going to be 1,020,000 joules. Okay. What's next? So times 1000. I'm just checking this in my calculator, make sure I don't make any mistakes. Good. So now we know the energy is 1,020,000 joules. The mass was 0.1 kilograms. Okay, so we sub those values in, and then L is what we don't know. So again, divide this by 0.1, and it gives you 10,200,000 equals L. Latent heat is always joules per kilo. Okay, so that's for this one up here. Last question, calculate the specific heat capacity of the substance in the liquid state. So before you melt, that's solid. After you melt it is liquid. And after you boil is gas. So it's referring to this section, because we're talking about the liquid state. Okay, so it's a change in temperature. So we would not use Q equals ml. That's just for when you're changing state. A change in temperature, we would use Q equals mc delta T. So again, do we know the energy? Not yet, but we can work it out easily. We've got the mass. We don't know the specific heat. And that's what it's asking you to find. And the change in temperature we do know, because it went from here 80 degrees up to here 150, so we got that. So we just need to find the heat first. So that took, it was liquid from 150 seconds to 180 seconds. So 30 seconds for this temperature rise. Okay, 30 seconds. It's a 1,000 watt source, so 1,000 joules per second times 30 seconds, that's 30,000 joules. Equals mass, so 0.1 kilos. Times C, which is, we don't know, that's what we're trying to find out, times the change in temperature. So 150 take 80. Okay, so that's 30,000 equals 0.1 times C times 150 take 80 is 70. So next, again, there's a few ways, but I'm just going to multiply the 0.1 times the 70 to turn that into one number. So then we've got 30,000 equals 0.1 times 70 is 7, and then C, 7C is the simplified version of that. Then divide both sides by 7. And that gives you 4,286 equals C. Now, specific heat capacity is always measured in joules per kilogram per Kelvin. And there we go. That's it.